Welcome to this fifth video on light. In this video, we will discuss total internal reflection in a prism. We have three different types of prisms: total reflecting prism or right-angled isosceles prism. Second is equilateral prism, and the third is right-angled prism. So we will discuss the behavior of light and total internal reflection happening in these three different prisms. So let's proceed. Total internal reflection through a right-angled isosceles prism. A prism having an angle of 90 degree between its two refracting surfaces and the other two angles each equal to 45 degree is called a total reflecting prism because the light incident normally on any of its faces suffers total internal reflection inside the prism. A total reflecting prism is used for the following three purposes. First, to deviate a ray of light through 90 degree. Second, to deviate a ray of light through 180 degree. And the third, to erect the inverted image without producing deviation in its path. So let us discuss these three different cases and let's see where these can be used. To deviate a ray of light through 90 degree. In figure, ABC is a total reflecting prism. A beam of light is incident normally at the face AB. It passes undeviated into the prism and strikes at the face AC at an angle of incidence equal to 45 degree. For glass-air interface, the critical angle is about 42 degree. Therefore, the beam of light suffers total internal reflection at the face AC because the angle of incidence is greater than critical angle. The reflected beam inside the prism then strikes the face BC, where it is incident normally and therefore passes undeviated. As a result, the incident beam gets deviated through 90 degree, emerging out through the prism. The figure shows the path of two rays PQ and P'Q' through the prism and then out of it. This action of prism is used in a periscope where a total reflecting prism is preferred over a plane mirror. The second case is deviation of a ray of light through 180 degree. In figure, the beam of light from the object PQ falls normally on the face AC of the prism, that is the hypotenuse. So, it enters undeviated inside the prism and strikes the glass-air interface AB of the prism. Since the beam of light is traveling from glass to air at an angle of incidence equal to 45 degree, which is greater than the critical angle 42 degree for glass-air interface. Therefore, the beam of light suffers total internal reflection. The reflected beam inside the prism strikes the face BC at an angle of incidence equal to 45 degree. So, it again suffers total internal reflection. The beam of light inside the prism now falls normally on the face AC and therefore passes undeviated out of the prism, forming the image P'Q' of the object PQ. The beam thus gets deviated by 90 degree at each reflection and the total deviation due to the two reflections becomes 180 degree. This action of prism is used in binoculars and camera to invert the image without the loss of intensity. And the third case is the erection of the inverted image without deviation. In figure, the beam of light from the object PQ is incident parallel to the face AC of the prism and strikes the face AB of the prism. It suffers refraction from air to glass and strikes the face AC of the prism, traveling from glass to air at an angle of incidence greater than the critical angle, which is 42 degree. Therefore, it suffers total internal reflection. The beam inside the prism now strikes the face BC at an angle of incidence less than the critical angle. Hence, it suffers refraction from glass to air and bends away from the normal. The beam emerges parallel to the face AC. As a result of refraction on emergence, the rays are inverted, and for the inverted object PQ, the erect image P'(Q') is obtained. A prism, when used in this manner, is called the erecting prism. This action of prism is used in a slide. The next category of TIR is through equilateral prism. A prism of each angle 60 degree can be used to deviate a light ray through 60 degree by total internal reflection. The figure shows a prism ABC of each angle 60 degree. A light ray PQ incident normally on the face AB of the prism passes undeviated as QR into the prism, and it strikes the face AC at an angle of incidence 60 degree at the point R. Now, the light ray QR suffers TIR at the glass-air interface, since the angle of incidence, which is 60 degree, is greater than the critical angle, which is 42 degree, such that angle QRS is 120 degree. The ray RS obtained after total internal reflection falls normally on the face BC of the prism, and so it passes out undeviated through the face BC. Thus, ST is the emergent ray. From the figure, it is clear that the incident ray PQ has turned through an angle of 60 degree towards the base from its initial direction, and it emerges out as ST. The third category is TIR through right-angled prism. Figure shows a prism ABC of an angle 30 degree, 90 degree and 60 degree. A light ray PQ incident normally on the face BC of the prism passes undeviated as QR into the prism, and it strikes the face AC at an angle of incidence 60 degree at the point R. Now the light ray QR suffers TIR at the glass-air interface, since the angle of incidence, which is 60 degree, is greater than the critical angle, which is 42 degree. The ray RS obtained after total internal reflection is incident at the face AB of the prism at an angle of incidence equal to 30 degree. This angle of incidence at glass-air interface is less than the critical angle. So, the ray RS is refracted from glass to air as ST with an angle of refraction greater than 90 degree. Thus, the emergent ray ST has turned through an angle of deviation which is less than 60 degree from the direction of incident ray PQ. Now in this clip, we will discuss non-occurrence of total internal reflection through a right-angled prism. But isn't it surprising that we discussed that there is going to be TIR in right-angled prism, and in this slide we are talking that it's not going to happen. But why is it so? Why dual behavior? It is simply, it depends upon the phase through which light is going to enter, the phase of the prism. So if you check out the diagrams, you will come to know why this different behavior. In figure A, a light ray PQ is incident normally on the face AB of the prism ABC, while in figure B, light ray PQ is incident on a part of face AC of the prism ABC. In both the cases, the light ray does not suffer total internal reflection inside the prism and gets refracted as RS, obeying the laws of refraction. In each case, the angle of incidence at the other face inside the prism is 30 degree, which is less than critical angle. Now here is an exceptional behavior of right angle prism. If you check out the B diagram of the previous slide and this diagram, you will note that the light is entering through the same face of the prism. Even then, the behavior of light is different in the two cases. Let's see how. A ray of light incident normally on hypotenuse of prism below the foot of the perpendicular on it from its opposite corner suffers TIR and gets deviated by an angle greater than 60 degree. In this figure, a light ray PQ is incident normally on the face AC of the prism in the portion DC such that the point D is the foot of perpendicular from B on AC. It passes undeviated as QR inside the prism and strikes the face BC of the prism at an angle of incidence 60 degree, which is greater than the critical angle 42 degree. The ray of light suffers TIR inside the prism as RS. The reflected ray RS then strikes the face AC at an angle of incidence 30 degree, so it suffers refraction from glass to air and emerges out of the prism as ST, bending away from the normal at the face AB. Thus, the incident ray PQ gets deviated through an angle greater than 60 degree. Distinction between the total internal reflection and reflection from a plane mirror. First, in total internal reflection, it takes place only when light passes from a denser medium to a rarer medium at an angle of incidence greater than the critical angle for that pair of media. Whereas, in reflection from a plane mirror, it takes place when light is incident on a plane mirror from any medium at any angle of incidence. In TIR, the entire light is reflected, whereas in reflection from a plane mirror, only a part of light is reflected while rest is refracted and absorbed. In TIR, there is no loss of energy. The energy of reflected ray is same as that of the incident ray. Whereas in reflection from a plane mirror, there is loss of energy. The energy of the reflected ray is always less than that of the incident ray. In TIR, the image is much brighter and the brightness remains unchanged even after the long use of the total reflecting device. Whereas in reflection from a plane mirror, the image is less bright and the brightness gradually decreases as the silvering on mirror becomes old and rough. So based on this, we can talk about use of total internal reflecting prism in place of a plane mirror. A total reflecting prism is used in a place of plane mirror to deviate the ray light by 90 degree in a periscope and by 180 degree in a binocular as well as in camera. The reason is that in TIR, the entire 100% light is reflected back into the denser medium, whereas in ordinary reflection from a plane mirror, some light is refracted and absorbed, so the reflection is not 100%. Thus, the image obtained by the use of a total reflecting prism is much brighter than that obtained by using a plane mirror. Further, the brightness of image formed by total reflecting prism always remains unchanged, while due to deterioration of a silvering of the plane mirror after a long use, the image formed by it becomes faint. Now let's talk about some consequences of TIR. You must have seen a diamond sparkling, right? So how come that diamond sparkles so much? A piece of diamond sparkles when viewed from certain directions, and this is happening because of TIR. An empty test tube placed in water in a beaker with mouth outside the water surface shines like a mirror when seen at certain angles, and this is also happening because of TIR. An optical fiber is used to transmit a light signal over a long distance without the loss of energy. And last but not the least, on a hot summer day, a driver may see a pool of water in front of him at some distance. It is the phenomenon of mirage, which is often observed in desert. And again, this is happening because of TIR. So kids, in these 5 videos, we have learned refraction of light at plane surfaces. And in the coming up videos, we'll be talking about refraction of light at curved surface. That is the concave and convex lenses. Till then, goodbye and take care of yourself. God bless you. Thank you.